The mystery of spacetime. What we use every day but don't understand. Tonight, I want to explore something that sounds straightforward but represents one of physics' deepest puzzles. What is spacetime? This term gets mentioned constantly in science discussions. You hear about Einstein's spacetime theories, the fabric of spacetime being warped, and how spacetime curves around massive objects. Yet here's the uncomfortable truth. When physicists examine what spacetime fundamentally is, they hit a wall. We simply don't know. This concept powers technologies you interact with daily. Your phone's navigation depends on it. Scientists have captured images of it bending around cosmic objects. We've measured vibrations traveling through it. Still, its fundamental nature escapes us. Tonight you'll discover why this ranks among the biggest unsolved problems in physics, and why cracking it could revolutionize our understanding of existence. Before we begin this exploration, I'd appreciate your support through likes and subscriptions. It genuinely helps grow this channel. Now, let's dive in. Einstein's revolutionary insight. Our story begins in 1905 with a 26-year-old patent clerk in Bern, Switzerland named Albert Einstein. He wasn't teaching at universities or leading research institutions. His day job involved reviewing patent applications for electromagnetic inventions. Physics was his evening pursuit, his passion outside regular work hours. That year, Einstein published 4 groundbreaking papers. One addressed Brownian motion, providing compelling evidence for atoms. Another explained the photoelectric effect, advancing quantum theory. 2 additional papers introduced special relativity, a framework that would transform our understanding of reality. Special relativity rests on a deceptively simple foundation. Light always travels at the same speed regardless of the observer's motion. This seems impossible initially. Consider being on a train travelling 100 kilometers per hour. Throw a ball forward at 20 kilometers per hour, and ground observers measure it moving at 120 kilometers per hour. Velocities combine. That's intuitive. Light behaves differently. Imagine travelling on a spacecraft at half light speed and shining a flashlight forward. Logic suggests the light would travel at 1.5 times light speed from an external observer's perspective. It doesn't. Both you and the external observer measure identical light speed, approximately 300,000 kilometers per second. Always the same. How can this be? How can light maintain constant speed for all observers when observers themselves move at vastly different velocities? Einstein's answer was radical. Space and time adjust themselves to preserve light's constant speed. When you move extremely fast, time genuinely slows down from a stationary observer's viewpoint. Distances along your direction of motion physically contract. These aren't illusions or measurement errors, they're real physical phenomena. Time and space aren't absolute and universal, they're relative, varying with motion. Only light speed remains absolute, identical for everyone regardless of their motion. This overturned centuries of assumptions. Newton had constructed physics on the premise that time flows uniformly for everyone, that 1 second equals 1 second everywhere, always. Einstein proved otherwise. Time flexes, space flexes, both bend according to motion. Consider the implications. Build a spacecraft travelling at 99% light speed and journey to a star 10 light-years distant and back. From your spacecraft perspective, perhaps only 2 years pass. Returning to Earth, however, 20 years have elapsed. Your friend's aged 20 years. Your children might now be older than you. This isn't speculation. Einstein's mathematics predict it, and experiments confirm it repeatedly. We've tested it with particle accelerators. Unstable particles, normally decaying in microseconds, survive much longer at near-light speeds. We've tested it with atomic clocks on aircraft. Flying an atomic clock around the planet and comparing it to an identical stationary clock reveals time differences, tiny, mere hundreds of nanoseconds, but measurable and matching Einstein's predictions precisely. The implications run deep. No universal now exists, no cosmic clock ticking uniformly everywhere. When you state something is happening right now on a distant planet, that statement lacks absolute meaning. Observers moving at different speeds disagree about simultaneity. Time isn't a river flowing steadily for everyone. It's more like a flexible medium that stretches and compresses based on your motion through it. The problem with gravity. But Einstein wasn't finished. Special relativity only addressed constant velocity motion. It couldn't handle acceleration or gravity, and gravity presented serious problems. Newton's gravitational law had worked brilliantly for over 2 centuries. It predicted planetary motion, projectile trajectories, and moon orbits with remarkable accuracy. It stood as one of history's most successful theories. Einstein realized it couldn't be completely correct. Newton's gravity worked instantaneously. If the sun vanished, Earth would immediately fly off into space according to Newton's equations. The gravitational influence would disappear instantly across 150 million kilometers, but Einstein had just demonstrated nothing travels faster than light. No signal, force, or information crosses space instantaneously. If the sun disappeared, light would stop reaching Earth after about 8 minutes, light's travel time from sun to Earth. Einstein recognized gravity couldn't propagate faster than light either. Delays must exist. Something must carry gravitational influence, and whatever it is can't exceed light speed. This led Einstein to his happiest thought, as he called it, in 1907. Sitting in his patent office, he imagined a worker falling from a roof. During the fall, Einstein realized the worker feels weightless. They're in free fall. Dropping a hammer while falling, the hammer floats alongside them, falling at the same rate. From the worker's perspective, the hammer hovers motionless. This seems obvious now. We've all seen astronauts floating aboard the International Space Station. But Einstein recognized something profound. The falling worker and the floating astronaut experience identical conditions. Both are in free fall. The astronaut isn't in zero gravity. They're falling toward Earth while moving sideways fast enough to continuously miss it. They're orbiting, perpetually falling but perpetually missing the ground. That's why they feel weightless, not from absent gravity but from free fall. Einstein realized free fall is indistinguishable from being in empty space without gravity. Being in an upward accelerating rocket is indistinguishable from standing on a planet's surface, feeling downward gravitational pull. In a windowless room, no experiment could determine whether you are on Earth's surface experiencing 1g of gravity or in a deep space rocket accelerating upward at 1g. The effects are identical. This is the equivalence principle. Acceleration and gravity are equivalent. They're the same thing. This insight unlocked general relativity. If acceleration and gravity are equivalent, and special relativity shows acceleration affects space and time, then gravity must also affect space and time. Gravity must curve space-time itself. 8 years of struggle. Working out the mathematics took Einstein another 8 years, from 1907 to 1915. He struggled with equations, learned advanced mathematics he'd never studied, made mistakes, published incorrect results, corrected them, and tried again. It became the hardest work of his life. The final year, late 1914 to November 1915, was the most exhausting and demanding period of his career. In November 1915, he finally perfected the equations. He published his general relativity theory, and physics transformed forever. General relativity states that mass and energy curve spacetime, and objects moving through curved spacetime follow curved paths, what we experience as gravity. It's not a force pulling objects together. Objects follow the straightest possible path through warped geometry. Those paths curve because the geometry itself curves. The standard analogy uses a rubber sheet. Stretch a flat rubber sheet taut. Place a heavy ball in the middle, creating a depression. Roll a smaller ball across the sheet. It curves toward the heavy ball, not because the heavy ball pulls it, but because the sheet itself is curved. The small ball attempts straight-line motion, but the curved sheet forces a curved path. This is what mass does to spacetime. The sun's enormous mass curves surrounding spacetime. Earth tries moving in a straight line through space, but curved spacetime around the sun forces Earth into a curved path. Earth's orbit. We experience this as the sun's gravity pulling Earth. From Einstein's perspective, there's no pull, just Earth moving through curved space-time. This rubber sheet analogy helps but misleads. The rubber sheet is two-dimensional, curving in three-dimensional space. Space-time is four-dimensional, 3 space dimensions plus 1 time dimension. It doesn't curve in some higher dimensional space. It curves in on itself. This is difficult to visualize because our brains evolved for 3 spatial dimensions, not 4-dimensional, space-time. Also, the rubber sheet makes gravity appear to pull balls downward, but that's Earth's gravity in the analogy. In real spacetime, no external force exists. The curvature itself is gravity. Objects follow geodesics, the straightest possible path through curved spacetime. A planet orbiting a star follows a geodesic, moving in what it perceives as a straight line. Because spacetime curves, that straight line curves back on itself, creating an orbit. The mathematics of curvature Einstein struggled for years finding the right mathematical language for these ideas. He needed tensor calculus, a mathematics branch dealing with multi-indexed objects that transform specifically when changing coordinate systems. He'd never studied this thoroughly during university. He learned it from his mathematician friend Marcel Grossman. Together they worked through the mathematics, trying different formulations, making errors, publishing preliminary versions that proved wrong. At one point Einstein thought he had correct equations, published them, then realized they didn't reduce to Newton's gravity in appropriate limits. That should have been a warning. Any new gravity theory must match Newton's predictions when gravitational fields are weak and objects move slowly, because Newton's theory works perfectly in those situations. Einstein's preliminary equations failed this test. He returned to the drawing board. The breakthrough came November 1915. Einstein was in Berlin, working feverishly. He delivered a lecture series at the Prussian Academy of Sciences, presenting weekly progress as he refined the theory. On November 25, 1915, he presented the final field equations, 10 interrelated equations describing how spacetime curvature is determined by mass and energy distribution. They're beautiful in their symmetry and elegance, written compactly as G + a sudden 8pt, where G is the Einstein tensor describing spacetime curvature and T is the stress-energy tensor describing mass, energy, momentum and pressure distribution. These equations look deceptively simple, but solving them for realistic situations is extraordinarily difficult. They're nonlinear partial differential equations. Curvature affects how mass and energy behave, but mass and energy also affect curvature, creating feedback loops making equations extremely hard to solve. For most realistic scenarios, exact solutions are impossible. You need numerical simulations on powerful computers. Even today, with modern computational power, solving Einstein's equations for complex situations like colliding black holes requires massive supercomputers running for weeks or months. Early successes. This was beautiful and elegant. It explained everything Newton's gravity explained, but more fundamentally, and made new predictions Newton's theory couldn't account for. One early success was explaining Mercury's orbit. Mercury, closest planet to the Sun, has an orbit slightly different from Newton's predictions. Mercury's closest approach point to the Sun shifts slightly with each orbit, called the precession of Mercury's perihelion. Astronomers had known this for decades without explanation. Some theorized another planet closer than Mercury, pulling on it and causing the shift. Einstein's equations predicted the exact precession amount without needing extra planets. Spacetime curved more strongly near the Sun, and that extra curvature explained Mercury's strange orbit perfectly. The real test came in 1919. Einstein's theory predicted light would bend under gravity. Specifically, starlight passing near the Sun would bend due to the Sun's curved spacetime. Stars would appear to shift position slightly when the Sun was nearby. But you normally can't see stars near the Sun. It's too bright, drowning out starlight. You can only see stars near the Sun during total solar eclipses when the Moon blocks sunlight. On May 29, 1919, a total solar eclipse occurred. 2 expeditions, one led by Arthur Eddington travelling to Principe Island off West Africa's coast, another to Sobral, Brazil, photographed stars during the eclipse. They measured star positions near the Sun and compared them to positions of the same stars photographed at night when the Sun wasn't nearby. The stars had shifted. Light bent under the Sun's gravity exactly as Einstein predicted. Measurements matched Einstein's equations. When results were announced in November 1919, Einstein became an overnight celebrity. Worldwide newspapers ran headlines about the eclipse results. Einstein's face appeared on magazine covers. He received lecture invitations everywhere. He went from respected physicist to the world's most famous scientist. By 1922, everyone in the physics community agreed Einstein had solved gravity. The problem was closed. The theory was complete, except it wasn't. The Schwarzschild solution. Einstein's equations were beautiful but difficult to work with. Most 1920s and 30s physicists couldn't solve them except in very simple cases. One simplest solution was found by Carl Schwarzschild in 1916, just months after Einstein published his theory. Schwarzschild was a German physicist serving in the German army during World War I. Despite being on the Russian front dealing with harsh 1916 warfare conditions, he found time for Einstein's equations. He solved them for the simplest possible case, a perfectly spherical, non-rotating mass sitting alone in empty space. The solution worked, describing how spacetime curves around a star or planet. But Schwarzschild noticed something strange in the mathematics. At a certain distance from the mass center, equations seemed to break, giving infinite values. They stopped making sense. This distance became known as the Schwarzschild radius. For the Sun, it's about 3 kilometers. For Earth, about 9 millimeters. These numbers seemed meaningless then because the Sun is much larger than 3 kilometers across. It has a radius of about 700,000 kilometers. Earth is much larger than 9 millimeters, with a radius of about 6,370 kilometers. The strange mathematical behavior only appeared deep inside the physical mass where the vacuum solution didn't apply anyway. Most physicists ignored it, just a mathematical quirk, an artifact of the idealized spherical solution. Nothing concerning. Schwarzschild himself died months after publishing his solution, contracting an autoimmune disease while serving on the Eastern Front. He died in May 1916 at age 42, never knowing how important his solution would become. For decades, the Schwarzschild radius remained a mathematical curiosity. Physicists knew about it, but didn't think it had physical significance. Einstein certainly wasn't worried. In fact, he actively disliked the implications. If you somehow compressed a mass smaller than its Schwarzschild radius, equations predicted something bizarre. Spacetime would curve so strongly nothing could escape, not even light. The object would become what we now call a black hole. At the center, all mass would collapse to an infinitely small point, a singularity where spacetime curvature became infinite, and physics laws broke down completely. Einstein thought this was absurd, revealing a theory limitation, not a reality prediction. He believed nature would never allow such a thing. He believed matter would resist such extreme compression. Some force, pressure, or quantum effect would prevent collapse beyond the Schwarzschild radius. The singularity was a mathematical artifact, not a real physical possibility, like dividing by zero in an equation. You get infinity, but that doesn't mean infinity exists in nature. It means you've pushed the equation beyond its validity domain. Most physicists agreed with Einstein. The idea of a star collapsing so completely it disappeared from the universe seemed ridiculous. The reality of black hole stars are held up by pressure. Hot gas pushes outward, balancing gravity's inward pull. When a star runs out of fuel, it cools, pressure drops and gravity takes over. But surely some force would stop the collapse. Perhaps electron degeneracy pressure, a quantum effect holding up white dwarf stars, or neutron pressure holding up neutron stars. Something would stop collapse. It had to. But in 1939, J. Robert Oppenheimer, who would later lead the Manhattan Project, and his student Hartland Snyder published a paper changing everything. They modelled a massive star running out of fuel, no longer able to support itself against gravity. They showed mathematically that for their idealized model, nothing could stop the collapse. No pressure or force was strong enough to halt it once started. The star would shrink past its Schwarzschild radius and keep shrinking until becoming a singularity, a point of infinite density where Einstein's equations themselves broke down. Later work showed this wasn't just true for idealized models. Even with realistic equations describing matter behavior under extreme pressure, sufficiently massive stars would still completely collapse. There's a mass limit beyond which no known force can prevent black hole collapse. Oppenheimer and Snyder didn't call it a black hole. That term wouldn't be coined until 1967 by John Wheeler. They just described gravitational collapse mathematics. But implications were clear. Einstein's own equations predicted stars could collapse into objects from which not even light could escape, objects where space-time became so warped it essentially sealed itself off from the rest of the universe. Einstein hated this result, thinking it showed general relativity must be incomplete, something missing from the theory. But he couldn't find flaws in Oppenheimer's mathematics. The equations were correct. General relativity really did predict these objects. Einstein died in 1955, never accepting. Black holes were real. For the next couple decades, most physicists remained skeptical. Black holes seemed too strange, too extreme, violating our intuitions about how the universe should work. But observations accumulated. In the 1960s, astronomers discovered quasars, incredibly bright objects in distant galaxies pouring out enormous energy from very small space regions. The only sensible explanation: supermassive black holes, millions or billions of times the Sun's mass, feeding on gas and dust. Material falling into the black hole would heat to millions of degrees and radiate energy before crossing the point of no return. Hawking radiation and the information paradox, theorists made progress understanding what black holes really meant for physics. In 1965, Roger Penrose proved a remarkable theorem. Once a star collapses past a certain point, singularity formation is mathematically unavoidable. It's not about the star being perfectly spherical or having special properties. Any collapsing star would form a singularity. Physics laws, as described by general relativity, literally forced it. Stephen Hawking extended this work. In the late 1960s and early 1970s, working with Penrose and others, he proved singularities are generic general relativity features. They don't just appear in black holes. The Big Bang itself, the universe's beginning, was a singularity, a point of infinite density and infinite curvature where time itself began. Hawking showed that running the universe's expansion backward in time, using Einstein's equations, you inevitably reach a singularity. There's no avoiding it within general relativity's framework. This was deeply troubling. General relativity had been incredibly successful describing gravity, spacetime, and object motion from planets to galaxies. But the theory itself predicted places where it broke down, giving infinite answers and stopping making sense. Singularities were like signs posted in the mathematics saying, "Beyond this point, physics doesn't work." Then in 1974, Hawking made another discovery shocking the physics community. Black holes aren't completely black. They emit radiation, Hawking radiation, from combining general relativity with quantum mechanics in a specific way. Here's how it works. Quantum mechanics says empty space isn't really empty. It's filled with quantum fluctuations, particle-antiparticle pairs popping into existence for incredibly brief moments, before annihilating each other. This happens everywhere, constantly. In normal space, far from black holes, these fluctuations are called virtual particles. They exist for such short times they can't be directly observed. They borrow energy from the vacuum, exist momentarily, then repay it by annihilating. Heisenberg's uncertainty principle in quantum mechanics allows this if it happens fast enough. Usually, these particle pairs appear and disappear so quickly they don't have observable large-scale effects. But near a black hole's event horizon, the point of no return, something different can happen. Imagine a virtual particle pair appearing right at the event horizon's edge. One particle appears just inside the horizon, the other just outside. Normally they'd annihilate almost instantly, but here the particle inside gets pulled in by the black hole's gravity before it can annihilate its partner. The particle outside escapes. To an outside observer, it looks like the black hole emitted a particle. But where did the energy for this real particle come from? From the black hole itself. When one particle of the virtual pair falls in, it has negative energy. From an outside observer's perspective, a strange general relativity consequence near black holes. The particle falling in reduces the black hole's mass very slightly. The escaping particle carries away positive energy. Total energy is conserved, but the black hole has lost mass. This process causes black holes to lose mass, slowly evaporating. Evaporation rate depends on black hole size. Smaller black holes evaporate faster because Hawking radiation temperature is inversely proportional to mass. A solar mass black hole would have a temperature of about 60 billionths of a degree above absolute zero. At that temperature, it would take about 10 to 67 years to completely evaporate, incomprehensibly long. The current universe age is only about 13.8 billion years. A solar mass black hole would take 10 to 1057 times the current universe age to evaporate. But a smaller black hole would evaporate much faster. A mountain mass black hole, about 1 billion metric tons, would have a temperature of about 100 billion Kelvin and evaporate in a fraction of a second, exploding in high-energy radiation. Tiny black holes, if they exist, would evaporate almost instantly, releasing tremendous energy. This was revolutionary. Black holes aren't eternal. They have finite lifetimes, eventually disappearing completely, evaporating away into radiation. And this created a new problem haunting physics for 50 years, the information paradox. The information paradox. Think about it like this. Imagine you write a book, a detailed information record, and throw it into a black hole. The book crosses the event horizon and falls toward the singularity. From outside, the book is gone. All you can observe about the black hole is its mass, spin, and electric charge. You can't tell what fell in. A book, rock, or star doesn't matter. The black hole looks the same regardless. In the 1970s, John Wheeler summarized this saying, "Black holes have no hair," meaning they have no features distinguishing what went into them. Now, if black holes were eternal, you might say the information is still there, locked inside forever, inaccessible but not destroyed. But Hawking radiation changes that. The black hole evaporates. Eventually it disappears completely, replaced by thermal radiation. Thermal radiation is random, not carrying information about what created it, like heat from a fire. You can't look at the heat and figure out what burned. This means the information about the book is destroyed. The words, ideas, specific particle arrangements making up the book, all gone. This violates a fundamental quantum mechanics principle called unitarity. Quantum mechanics says information is never destroyed. It can be scrambled, spread out, hidden in incredibly complex ways, but it's always there in principle. If you knew every particle's quantum state perfectly, you could reconstruct the past or predict the future with perfect accuracy. Information is conserved. But Hawking radiation seemed to destroy information. The book's quantum state is lost forever, as if the book was erased from universe history. This created deep conflict between general relativity and quantum mechanics. One had to be wrong, or our understanding of both had to be incomplete. Physicists debated this for decades. Hawking initially argued information really is destroyed in black holes, that quantum mechanics breaks down in extreme gravitational fields. Others argued information must be preserved somehow. We just don't understand the mechanism yet. The paradox remained unsolved, signaling something was fundamentally wrong with our spacetime understanding. Technologies built on mystery. Before we go further into the mystery, let's appreciate something remarkable. This idea we don't fully understand. This theory breaking down at singularities and possibly destroying information. We use it every single day. General relativity isn't just abstract theory for understanding black holes and the Big Bang. It affects your life in concrete, practical ways. Start with the most obvious example, GPS. Your phone, your car's navigation system, any device telling you where you are, uses a network of satellites orbiting Earth about 20,000 kilometers up. These satellites constantly broadcast signals containing exact time, according to onboard atomic clocks and position information. Your GPS device receives signals from at least 4 satellites, measures signal arrival times, and uses that information to calculate your position. Light speed is constant. If you know how long a signal took to arrive and know it travelled at light speed, you can calculate satellite distance when it sent the signal. With signals from 4 satellites, you can pinpoint your 3-dimensional position through simple geometry. But there's a problem. Atomic clocks on satellites don't tick at the same rate as ground clocks. 2 general relativity effects work here. First, satellites move at about 14,000 kilometers per hour relative to the ground. According to special relativity, time runs slower for moving objects. From a ground perspective, satellite clocks should tick slightly slower, time dilation due to velocity. The effect is tiny but measurable. Satellite clocks lose about 7 microseconds per day compared to ground clocks. But there's a second, larger effect. Satellites are higher in Earth's gravitational field, farther from Earth's mass center, experiencing weaker gravity. According to general relativity, time runs faster in weaker gravitational fields. From a ground perspective, satellite clocks should tick slightly faster, gravitational time, dilation. Satellite clocks gain about 45 microseconds per day compared to ground clocks. Adding these effects together, satellite clocks run about 38 microseconds per day faster than ground clocks. That doesn't sound like much, 38 microseconds. But light travels about 300 meters in 1 microsecond. If GPS didn't correct for these relativistic effects, your position would be off by about 11 kilometers per day. Within hours, GPS would be completely useless, telling you you're in the wrong city. GPS designers knew this, They programmed satellite clocks to tick at slightly different rates to compensate for relativity. Every GPS calculation accounts for Earth's spacetime curvature. Every time you use GPS to navigate, you're relying on Einstein's equations. You're using general relativity. And it works. It works perfectly. But do we understand what spacetime actually is? No. We just know how to calculate its effects. Here's another stranger example. Gold. The metal gold has a distinctive yellow colour, the only metal looking yellow. Silver is silvery white. Copper is reddish. Iron is grey. But gold is yellow. Why? The answer involves relativity. Atoms absorb and emit light at specific frequencies depending on electron energy levels. For most metals, absorbed light frequency is in the ultraviolet range, higher energy than visible light. So they reflect all visible light and appear silvery or grey. Gold is different. Gold atoms are heavy with 79 protons in the nucleus, creating a strong electric field. The innermost electrons move very fast in this strong field, fast enough that relativistic effects become important. According to special relativity, as electrons move faster, their mass effectively increases. This changes atom energy level spacing. For gold, this relativistic effect shifts energy levels enough that gold absorbs blue light instead of ultraviolet. When white light hits gold, blue frequencies are absorbed and remaining reflected light is yellow. Gold's colour is a relativistic effect. Without special relativity, gold would look silvery like most other metals. The same happens with mercury. Mercury is the only room temperature liquid metal. Why? Again, relativity. Mercury atoms have 80 protons, and innermost electrons move so fast that relativistic effects make bonds between mercury atoms weaker than they'd otherwise be. Atoms don't stick together as strongly, so mercury melts at much lower temperature than expected. Without relativity, mercury would be room temperature solid, and thermometers would work very differently. These aren't just curiosities. These are real, measurable relativity effects in everyday materials. The universe we live in, the element properties around us, are shaped by spacetime curvature and time flexibility. We use these effects without thinking about them, detecting gravitational waves. Even more impressive is LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO is designed to detect gravitational waves, space-time ripples caused by violent cosmic events like colliding black holes or neutron stars. These ripples stretch and squeeze space as they pass through. The effect is incredibly small. When a gravitational wave passes through Earth, it might change the distance between 2 points separated by 4 kilometers by less than 1/10,000th the width of a proton. Let me put that in perspective. A proton is about 10 real, 15 meters across. 1/10,000th of that is 10 real, 19 meters. LIGO detectors can measure distance changes that small. To give you a sense of scale, if the distance between Earth and the nearest star, Proxima Centauri, about 40 trillion kilometers, changed by a human hair's width, LIGO would detect it. LIGO detects this by splitting a laser beam, sending the halves down perpendicular 4-kilometer tunnels, bouncing them off mirrors at the ends and recombining them. If a gravitational wave passes through while light is travelling, one detector arm stretches slightly while the other squeezes slightly, creating a tiny change in light travel time down each arm. When beams recombine, they create an interference pattern revealing the passing wave. The first detection happened September 14, 2015, LIGO's first science run day after a major upgrade. The signal arrived at the Louisiana detector at 5:51 a.m. Central Daylight Time. 7 milliseconds later, it arrived at the Washington State detector. The signal lasted about 1/5 second, starting at about 35 Hz frequency and rising quickly to about 250 Hz before cutting off abruptly. This pattern exactly matched expectations from two black holes spiraling into each other and merging. Analysis showed the two black holes each had about 30 times the Sun's mass. They'd been orbiting each other for billions of years, gradually spiraling inward as they lost energy to gravitational waves. In the final fraction of a second, they orbited each other hundreds of times per second, moving at significant fractions of light speed. When they merged, the collision released more energy in a fraction of a second than all observable universe stars emit in the same time. About 3 solar masses worth of energy, equivalent to annihilating 3 suns and converting all their mass directly to energy, radiated away as gravitational waves in less than a second. That energy radiated outward at light speed as spacetime ripples. The event happened 1.3 billion light-years away, so waves took 1.3 billion years reaching Earth. When they arrived, they stretched and squeezed LIGO's 4-kilometer arms by about 1,000th of a proton's width, and LIGO detected it. The discovery was announced February 11, 2016, after months of careful analysis ensuring the signal was real, not some instrumental artifact or noise. It was front page worldwide, news confirming a major general relativity prediction never directly tested before. Since then, LIGO and sister observatories, Virgo in Italy and Kaga in Japan, have detected dozens of gravitational wave events. Most are from merging black holes. Some are from merging neutron stars. Each detection teaches us something new about these extreme objects and gravity's nature itself. In August 2017, LIGO and Virgo detected gravitational waves from 2 neutron stars merging about 130 million light-years away. This event was special because neutron star mergers also produce light. Unlike black holes, which are dark, neutron stars are made of normal matter and glow. When they merge, they create a bright explosion called a kilonova. Within seconds of gravitational wave detection, LIGO sent alerts to worldwide astronomers. Telescopes swung into action, searching the signal's sky region. Within hours, they found it, a new bright source in galaxy NGC 4993. Over following days and weeks, dozens of telescopes observed the kilonova at different wavelengths from gamma rays to radio waves. It was the first time humanity observed a cosmic event with both gravitational waves and light. The dawn of multi-messenger astronomy. Observations confirmed something physicists long suspected. Heavy elements like gold, platinum, and uranium are created in neutron star mergers. The collision creates conditions so extreme that atomic nuclei are smashed together and rebuilt into heavy elements. The kilonova ejected about 1/100th of a solar mass of material, much of it gold and platinum. All gold on Earth, every gold ring, every gold coin, every gold bar in bank vaults, was created in neutron star mergers billions of years ago before the solar system formed. The gold was scattered into space, mixed with gas and dust, and eventually incorporated into the material disk that formed the sun and planets. When you wear a gold ring, you're wearing atoms forged in neutron star collisions, photographing black holes. Then there are black hole photographs. In April 2019, the Event Horizon Telescope collaboration released the first black hole image. It wasn't a traditional photograph, it was radio telescope data from worldwide observatories combined using a technique called very long baseline interferometry. 8 radio telescopes spread across the planet, from Hawaii to Antarctica, from Spain to Chile, all pointed at the same target simultaneously, recording radio waves at 1.3 mm wavelength, a frequency where gas around black holes glows brightly. The technique works by combining signals from all telescopes as if they were parts of a single Earth-sized telescope. Telescope resolution depends on size. Larger telescopes see finer details. By spreading telescopes across the planet and combining signals, you achieve resolution equivalent to a telescope about 13,000 kilometers across. That's enough resolution to read a newspaper in New York from a Paris cafe, or see an orange sitting on the moon's surface. But the process is incredibly difficult. You need atomic clocks at each telescope to precisely timestamp signal arrivals. You need to record petabytes of data, so much it couldn't be sent over the internet. Hard drives had to be physically shipped to a central processing facility. You need to correct for Earth's rotation, atmospheric effects, and telescope motion. And you need to do all this for signals from billions of kilometers away, so faint they're almost lost in noise. The result was an image showing a light ring around a dark circle. The black hole was in galaxy Messier 87's center, about 55 million light-years away. The black hole itself is about 6.5 billion times the Sun's mass. The dark region in the image center, the shadow, has a diameter of about 40 billion kilometers, about 3 times Pluto's orbit size around the Sun, and it's completely dark because it's the event horizon. No light escapes from inside, the light ring around. The shadow is gas orbiting the black hole at speeds approaching light speed. The gas is heated to billions of degrees by friction and magnetic fields, glowing in X-rays, visible light, and radio waves. The light we see has been bent by extreme space-time curvature around the black hole. Some photons orbit the black hole multiple times before escaping. Some are bent just enough to reach our telescopes. The ring appears brighter on one side because the gas is rotating. On one side, it's moving toward us, and relativistic effects make it appear brighter. On the other side, it's moving away and appears dimmer. What you're seeing in that image is not the black hole itself. The black hole is the dark circle in the center, the region from which no light escapes. What you're seeing is the black hole's effect on surrounding spacetime. Light from hot gas is being bent, twisted, focused by curved spacetime. The image is a direct photograph of Einstein's predictions. The shadow size, ring shape, and brightness distribution all match computer simulations based on general relativity. In May 2022, the collaboration released a second black hole image, this one at our own galaxy's center, Sagittarius AE. It's about 4 million times the Sun's mass, much smaller than the Messier 87 black hole, but much closer, only about 27,000 light-years away instead of 55 million. Again, the image shows a light ring around darkness. You're looking at curved spacetime. You're seeing photons bent by gravity on their journey to Earth. The three big questions. We use this idea every single day, in GPS, in gold's color, in Mercury's liquidity, in fiber optic networks, in gravitational wave detectors, in black hole photographs. We've built entire technologies on Einstein's framework. That's both amazing and unsettling. It's like discovering your house rests on an invisible foundation. You can measure how it responds to weight, calculate how it bends under stress, predict how it will behave, but the material itself remains unknown. So let's dig into the mystery. What exactly don't we understand about spacetime? The answer isn't simple, but it breaks down into three big questions. Three places where our knowledge hits a wall. Three puzzles that, if we could solve them, would revolutionize physics and possibly technology. Question 1. What is spacetime made of? Let's start with the most basic question. What is spacetime? Einstein's equations describe how spacetime curves in response to mass and energy. They tell us how to calculate curvature given matter distribution. They predict how objects move through curved spacetime. But they don't tell us what spacetime actually is. In Einstein's theory, spacetime is treated as a smooth continuum. You can zoom in on any space point and there's always more space at smaller scales. You can divide time into smaller and smaller intervals and there's always more time. Space and time are continuous, infinitely divisible. This works perfectly for calculations at observable scales. But there's reason to believe this can't be the whole story. Quantum mechanics, the theory describing particle behavior at very small scales, says almost everything in nature is discrete, quantized, coming in chunks rather than being continuous. Energy comes in chunks called quanta. Light comes in chunks called photons. Even electron spin comes in discrete values. You can't have half a photon or an electron spinning at arbitrary angles. The quantum world is fundamentally grainy, not smooth. This suggests space and time might also be quantized at very small scales. There might be a smallest possible length, a space quantum. There might be a smallest possible duration, a time quantum. Below these scales, talking about smaller distances or shorter times doesn't make sense. Space and time would be fundamentally discrete, like a digital photograph made of pixels rather than a continuous analog image. This scale is called the Planck length, about 10 to 35 meters. To give you a sense of how small this is, a proton is about 10 to 15 meters across. The Planck length is 20 orders of magnitude smaller than a proton. If you scaled a proton up to the observable universe's size, the Planck length would be about tree-sized. At this scale, quantum effects on spacetime itself should become important. The smooth spacetime fabric Einstein described should break down into something else, something grainy, something chaotic. Physicists call this quantum foam, the idea that zooming in far enough spacetime would look turbulent, bubbling with quantum fluctuations constantly forming and dissolving tiny structures. But we have no direct way to probe these scales. The Planck length is so small we can't build experiments to measure it. The energies required to probe Planck-scale physics would be about 10 to 19 giga-electron-volts. The Large Hadron Collider, the most powerful particle accelerator ever built, reaches energies of about 14,000 giga-electron-volts. To probe the Planck scale, you'd need an accelerator about 10,000 trillion times more powerful, far beyond anything we could possibly build with foreseeable technology. So we're stuck trying to figure out what happens at these scales using pure theory, mathematics, and indirect reasoning. And there are several competing ideas, none we can test directly. Loop quantum gravity. One leading candidate is loop quantum gravity. This approach takes Einstein's equations and tries to quantize them directly. Instead of treating spacetime as a smooth continuum, loop quantum gravity says spacetime is made of discrete chunks connected in a network. Space is woven from loops, tiny spacetime loops about a Planck length in size. These loops connect to form a network, and spacetime geometry emerges from how these loops are arranged and connected. In this picture, area and volume are quantized. You can't have arbitrary area or volume. They come in discrete units, multiples of the Planck length squared or cubed. Spacetime has a minimum possible volume you can't divide smaller. This solves some problems. It suggests singularities might not actually exist at black hole centers or at the Big Bang. Instead of collapsing to infinitely small points, matter would collapse to minimum volumes set by quantum effects. The singularity would be replaced by a quantum bounce or some other structure. But loop quantum gravity has problems. It's mathematically very complex, and it's hard to extract testable predictions. It also hasn't been successfully unified with other nature forces or with quantum field theory, the framework describing how particles interact. It's a quantum gravity theory, but it's unclear how to incorporate electromagnetic force, weak nuclear force, or strong nuclear force into the same framework. String theory. Another approach is string theory. String theory says nature's fundamental objects aren't point particles but tiny vibrating strings. Different string vibrations correspond to different particles. An electron is one vibration, a photon is another, a quark is another, and one particular vibration corresponds to the graviton, the hypothetical quantum particle carrying gravitational force. In string theory, spacetime emerges from string interactions. The strings exist in higher dimensional space, usually 10 or 11 dimensions rather than the 4 we experience, 3 space, 1 time. Extra dimensions are curled up so small we don't notice them, compactified at scales near the Planck length, and spacetime geometry, the curvature we experience as gravity, comes from how strings move and interact in this higher dimensional space. String theory is elegant in many ways. It naturally includes gravity. Unlike other quantum gravity attempts that run into mathematical inconsistencies, string theory is mathematically consistent. It unifies all forces, electromagnetism, weak nuclear force, strong nuclear force, and gravity all emerge from the same framework, from strings vibrating in different ways. It has rich mathematical structure deeply interconnected with advanced mathematics. Mathematicians have discovered new theorems and connections in pure mathematics by studying string theory. The theory emerged in the 1970s initially as an attempt to describe the strong nuclear force. That didn't work out, but physicists realized the theory naturally contained a gravity description. In the 1980s and 90s, string theory experienced rapid development. Physicists discovered 5 different string theory versions, all mathematically consistent but apparently different. This was puzzling. If string theory was nature's fundamental theory, there should only be one version. Then in 1995, Edward Witten proposed all 5 versions were actually different limits of a single, more fundamental theory he called M theory. M theory works in 11 dimensions, 10 space, 1 time. The 5 string theories are different ways of looking at this same underlying theory. It was a major unification, suggesting string theory might truly be unique. String theory has made concrete beyond standard model physics predictions. It predicts supersymmetry, a hypothetical symmetry relating particles of different spins. For every known particle, there should be a supersymmetric partner. The electron would have a partner called the selectron. Quarks would have partners called squarks. Photons would have partners called photinos. If supersymmetry exists, it would solve several particle physics problems and provide a natural dark matter candidate. But here's the problem. We've searched extensively for supersymmetric particles at the Large Hadron Collider and haven't found any. The LHC has probed energies up to about 14,000 giga-electronvolts, creating collisions energetic, enough that supersymmetric particles should have been produced if they exist at accessible energies, but we haven't seen them. This doesn't completely rule out supersymmetry. The particles might be heavier than we can produce, but it's disappointing. String theory led us to expect supersymmetry at energies we could reach, and it's not there. String theory also has another serious problem. There are an enormous number of possible string theories, depending on how you curl up the extra dimensions. The extra 6 or 7 dimensions can be compactified in many different ways. Each way gives you a different 4-dimensional theory with different particles and forces. Current estimates suggest there might be 10,500 different versions, maybe more. This is called the landscape problem. 10,500 is incomprehensibly large, far more than the number of atoms in the observable universe, which is only about 10 to 80. With 10,500 possible string theories, how do we know which one describes our universe? There's no principle within string theory selecting one vacuum over another. Some physicists have argued maybe all these vacua are real, each describing a different universe in a vast multiverse. Our universe just happens to be one particular landscape point. We exist in this particular universe because physical constants happen to allow stars, planets, and life to form. In other universes with different constants, life might not be possible, so there's no one there to observe them. This anthropic reasoning troubles many physicists. It seems to give up on explaining why physics laws have their specific form. Instead, it says laws are essentially random, different in different universes, and we live in one of the rare universes where laws allow life. It's not a satisfying explanation. It doesn't predict anything. It can't be tested. You can't observe other universes forever beyond our cosmic horizon. And there's an even more fundamental string theory problem. It makes almost no testable predictions at energies we can reach with current or foreseeable technology. String theory's natural scale is the Planck energy, about 1019 giga-electron volts. The LHC reaches energies of about 10.4 giga-electron volts. To probe the Planck scale directly, we'd need an accelerator 10,000 trillion times more powerful than the LHC. Building such a machine is far beyond our technological capabilities. It might be beyond any civilization's capabilities bound by physics laws as we understand them. Without testable predictions, how do we know string theory is right? It's mathematically beautiful, logically consistent, unifying forces elegantly. But beauty and elegance aren't truth-proof. History is full of beautiful theories that turned out wrong. Physics requires experimental verification. We need to test theories against reality. And for string theory, that's incredibly difficult, maybe impossible. Some physicists argue string theory has become more mathematical framework than physical theory. It's produced important insights into mathematics and theoretical physics. It's given us tools for quantum field theory calculations. It's revealed deep connections between different physics and mathematics areas. But as a fundamental reality theory, as a quantum gravity theory explaining what spacetime really is, it remains unproven. It might be a beautiful mathematical structure having nothing to do with how the universe actually works. Emergent spacetime. There's also a more radical idea gaining traction in recent years. Maybe spacetime isn't fundamental at all. Maybe space and time are emergent properties arising from something deeper, something not looking like space or time at all. This is the idea behind approaches like unsettling, EPR, named after Einstein-Rosen bridges, and Einstein-Podolsky-Rosen correlations. Here's the basic idea. Quantum mechanics allows a strange phenomenon called entanglement. Two particles can be entangled such that measuring one instantly affects the other, no matter how far apart they are. This isn't faster-than-light communication because you can't control your measurement outcome, but it is a correlation existing across space without anything travelling through the space between. In 1935, Einstein and two colleagues wrote a paper describing this phenomenon and arguing it showed quantum mechanics was incomplete. They thought correlations must be explained by hidden information particles, carried with them. But experiments have shown correlations are real and can't be explained by hidden information. Entanglement is a genuine quantum mechanics feature. Also in 1935, Einstein and Nathan Rosen wrote a paper about general relativity solutions containing wormholes, space-time shortcuts connecting distant regions. These became known as Einstein-Rosen bridges. But the wormholes in their solution were unstable, collapsing before anything could pass through. In recent years, physicists have wondered if there might be a connection between entanglement and wormholes. The idea is summarized by the equation EPR, where ER stands for Einstein-Rosen bridges and EPR stands for Einstein-Podolsky-Rosen entanglement. The suggestion is that when two particles are entangled, They're connected by a tiny wormhole, a spacetime thread linking them. If this is true, it would mean spacetime itself is woven from entanglement. The connections between distant space points, the geometry we think of as spacetime, would emerge from quantum correlations between particles. Space would be an illusion, a useful way of describing something more fundamental. Distance would emerge from the entanglement pattern. This is speculative. It's not a complete theory, but it's motivated by serious theoretical work and by discoveries about black holes and entanglement. And it points to a possibility that's both exciting and unsettling. Everything we think we know about space and time might be wrong at a fundamental level. They might not be reality's basic building blocks. They might be emergent, appearing only at large scales, like how gas temperature and pressure emerge from individual molecule motion. The bottom line is this. We don't know what spacetime is made of. We have equations describing how it behaves. We can measure its curvature. We can detect waves moving through it. But the fabric's fundamental nature itself remains a mystery. Question 2. What happened at the Big Bang? When we run the universe's expansion backward in time using Einstein's equations, we inevitably reach a point where the entire universe was compressed into an infinitely small, infinitely dense singularity. This is called the Big Bang singularity. The beginning of time, the birth of space, matter and energy all at once. But calling it a singularity is another way of saying the equations break down. At the singularity, density becomes infinite, temperature becomes infinite, space-time curvature becomes infinite. Anything divided by 0 or multiplied by infinity gives nonsense. The mathematics stops working. And that means we don't actually know what happened. We have very good evidence for the Big Bang in a general sense. The universe is expanding. We can measure the expansion. We see galaxies moving away from us in all directions. When we measure distant galaxy light, we find it's redshifted, wavelength stretched because space between us and those galaxies has been expanding while light travelled toward us. The farther away a galaxy is, the more its light is redshifted, meaning the faster it's moving away. This relationship was discovered by Edwin Hubble in 1929 and is one of cosmology's foundational observations. If the universe is expanding now, it must have been smaller in the past. Run the clock backward, and everything gets closer together. Temperatures and densities increase. Eventually, you reach a point about 13.8 billion years ago when the universe was incredibly hot and dense. We call this the Big Bang, but that's a bit misleading. It wasn't an explosion in space. It was an expansion of space itself. We have other evidence too. In 1964, Arno Penzias and Robert Wilson discovered the cosmic microwave background radiation. They were working at Bell Labs in New Jersey, using a large horn antenna built for satellite communications. They were trying to measure radio signals from the Milky Way but kept detecting annoying background noise that wouldn't go away. No matter which direction they pointed the antenna, no matter what time of day or night, the noise was always there. At first they thought it might be interference from New York City, but the signal had the same intensity from all directions. They thought it might be heat from the ground or atmosphere, but the signal had the wrong spectrum for thermal emission from Earth. They even cleaned the antenna thoroughly, removing bird droppings, but the signal persisted. Finally, they learned theoretical physicists at Princeton, just kilometers away, had predicted exactly such a signal. If the universe had started in a hot, dense state and expanded and cooled, there should be leftover radiation from that early hot phase. The radiation would have been stretched by universe expansion from high-energy gamma rays down to microwave frequencies, and it should be coming from all directions uniformly because the early universe was nearly uniform, everywhere. Penzias and Wilson had accidentally discovered Big Bang proof. The cosmic microwave background is light left over from when the universe was only about 380,000 years old. Before that time, the universe was so hot that atoms couldn't form. Temperature was over 3000 Kelvin. At that temperature, electrons have enough energy to escape atomic nuclei. Electrons and protons existed separately as hot plasma. In this plasma state, light couldn't travel far. Photons would constantly scatter off free electrons, bouncing from electron to electron like a ball in a pinball machine. The universe was opaque, like being inside thick fog. You couldn't see through it because light was constantly being absorbed and re-emitted by plasma. But as the universe expanded and cooled, eventually temperature dropped below 3000 Kelvin. At this point, Electrons and protons could combine to form neutral hydrogen atoms. This happened rather suddenly across the entire universe, a transition called recombination. Suddenly, light could travel freely. The universe became transparent. Photons could stream through space without being scattered. Those photons have been travelling ever since, stretched by universe expansion from visible light, with wavelengths of about 500 nanometers to microwave radiation, with wavelengths of about 2 millimeters. The redshift factor is about 1/100. The universe has expanded by a factor of 1/100 since recombination. We can detect this radiation today, coming from every sky direction. It's a nearly uniform glow with a temperature of about 2.725 Kelvin, just a few degrees above absolute zero. But it's not perfectly uniform. There are tiny variations, slight temperature differences from one direction to another. Some regions are slightly warmer, about 2.72 Kelvin. Some are slightly cooler, about 2.72245 Kelvin. The variations are only about 1 part in 100,000, incredibly small, but real and incredibly important. These variations are the seeds of universe structure. Regions that were slightly denser had slightly higher temperatures. These regions had slightly stronger gravity. Over billions of years, matter was pulled into these slightly denser regions by gravity. Dense regions became denser. Less dense regions became emptier. Over time, tiny variations grew into the galaxies, galaxy clusters, and superclusters we see today. Every galaxy, every star, every planet, including Earth, exists because of tiny quantum fluctuations in the early universe that left their imprint on the cosmic microwave background. We've mapped these temperature variations with incredible precision using satellites. The COBE satellite in the early 1990s made the first detections. The WMAP satellite from 2001 to 2010 mapped the sky in much higher resolution. The Planck satellite from 2009 to 2013 produced the most detailed map yet, measuring temperature variations across the entire sky with a resolution of about 5 arc-minutes, about 1/6 the full moon's width. From these maps we can determine fundamental universe properties, the age, currently 13.8 billion years, the composition, about 5% normal matter like atoms, about 27% dark matter we can't see directly, but which has gravitational effects, and about 68% dark energy causing expansion to accelerate. Space geometry, which appears flat, meaning parallel lines stay parallel forever rather than converging or diverging. And the expansion rate, the Hubble constant, telling us how fast galaxies are receding from each other. All this from studying tiny temperature variations in ancient light. The cosmic microwave background is one of the most important Big Bang evidence pieces. It's a snapshot of the universe when young, and it matches Big Bang cosmology predictions in incredible detail. We can calculate what temperature variation should look like based on our theories of how the early universe evolved, run computer simulations, and compare to observations. The match is extraordinarily good. Modern cosmology can explain patterns we see to better than 1% precision. But when we try understanding the very beginning, the first moments, we run into problems. Einstein's equations predict a singularity. But singularities are places where theory breaks down. At the Planck time, about 10⁻43 seconds after the Big Bang, quantum effects on spacetime should become important. Below this timescale, general relativity can't be trusted. We need a quantum gravity theory, and we don't have one. The best we can do is patch the problem with a theory called cosmic inflation. Inflation was proposed in the early 1980s by Alan Guth and others. The idea is that in the very early universe, there was a brief period when space expanded exponentially fast. In a tiny fraction of a second, the universe grew by a factor of at least 10⁻26, a region smaller than a proton inflated to grapefruit size or larger. This solves several problems. It explains why the universe looks so uniform in all directions. Regions of space now billions of light-years apart were once close enough to interact and reach the same temperature. It explains why space appears flat rather than curved. Any initial curvature would have been stretched out by rapid expansion, just like a balloon's surface looks flatter the more you inflate it. And it explains structure origin. Quantum fluctuations during inflation would have been stretched to cosmic scales, creating the tiny density variations we see in the cosmic microwave background. Inflation is supported by observations. Cosmic microwave background patterns match inflation predictions. But inflation doesn't solve the singularity problem, it just pushes it back. Inflation requires very specific initial conditions. You need a particular kind of energy field to drive expansion, and you need the universe to start in a special state for inflation to work. Where did those conditions come from? We don't know. And if you trace inflation back far enough, you still reach a singularity where equations break down. Some physicists have proposed alternatives. One idea is that the Big Bang wasn't the beginning. Maybe the universe bounced. Maybe it was contracting before the Big Bang and then bounced at minimum size, transitioning from contraction to expansion. This would require quantum effects to stop collapse before reaching a singularity, creating a quantum bounce. Loop quantum gravity suggests this might happen, but the mathematics isn't yet fully worked out. Another idea is that the universe didn't begin from a singularity at all, but emerged from nothing through a quantum process. This gets into deep philosophical territory about what nothing means. In quantum mechanics, empty space isn't really empty. It's filled with quantum fluctuations, virtual particles popping in and out of existence. Some models suggest the universe could have emerged from a vacuum quantum fluctuation, a spontaneous creation event allowed by quantum mechanics. But all these ideas are speculative. We don't have a complete theory describing universe origin. We don't know what happened at the Big Bang singularity, or whether there even was a singularity. General relativity equations point to a beginning, but they also tell us they can't be trusted at the very beginning. It's like a map showing you how to get somewhere but has a blank spot at the destination labelled "Here be dragons." The Big Bang question remains one of physics' deepest mysteries. We know the universe had a beginning. We know it was once incredibly hot and dense. We know it's been expanding for about 13.8 billion years. But the very first moment, the beginning's nature itself is hidden behind an ignorance wall. We need a quantum gravity theory to go further, and we don't have one. Question 3. Do black holes destroy information? The third big question brings us back to black holes, and the information paradox. Do black holes destroy information? This might sound like an abstract philosophical question, but it cuts to the heart of how the universe works at the deepest level. In quantum mechanics, quantum system evolution is described by the Schrödinger equation. This equation is deterministic. If you know a system's quantum state at one time, you can calculate its state at any other time, past or future. Information is conserved. The quantum state carries a complete system description, and that information never disappears. It might get scrambled, spread out among many particles in complex ways, but it's always there in principle. This is called unitarity, a fundamental quantum mechanics principle. Processes are reversible. If you know the final state perfectly and run equations backward, you can recover the initial state. Information is never lost. But Hawking radiation seems to violate this. When a black hole evaporates, it emits thermal radiation carrying no information about what fell in. Thermal radiation is characterized only by temperature. It's random. If you collect all Hawking radiation from an evaporated black hole, you can't reconstruct what went in. The information is gone. To make this concrete, imagine you write a book and throw it into a black hole. The book has information, the specific word arrangement on each page, precise positions of all atoms making up paper and ink. In principle, if you knew the book's quantum state perfectly, you could describe it with complete precision. Now the book crosses the event horizon and falls toward the singularity. From outside, the black hole has gained a tiny bit of mass equal to the book's mass, but you can't tell what fell in. The black hole doesn't carry any trace of the words on pages. Now wait. The black hole slowly evaporates via Hawking radiation. After a very long time, much longer than the current universe age for any significant size black hole, the black hole disappears completely. All that's left is a cloud of photons and other particles, random thermal radiation. Can you reconstruct the book from this radiation? According to Hawking's calculation, no. The information is lost. The words are gone forever. This creates a paradox. Either quantum mechanics is wrong and information can be destroyed, or general relativity is wrong and black holes don't actually destroy information. Or both theories are incomplete and something else is going on we don't understand. For decades, physicists debated this. Hawking argued information really is lost, that quantum mechanics breaks down in extreme gravitational fields. Others, including Leonard Susskind and Gerard Hooft, argued information must be preserved. We just don't understand the mechanism. The debate was fierce, becoming known as the Black Hole War. One key insight came from the holographic principle, the idea that all information about what's inside a black hole is somehow encoded on its event horizon, the surface marking the point of no return. Event horizon area is proportional to the black hole's entropy, a measure of how much information it contains. This suggested information isn't lost inside the black hole but is stored on the surface in scrambled form. The holographic principle was inspired by Jacob Bekenstein and Stephen Hawking's work on black hole thermodynamics. They showed black holes have entropy proportional to event horizon area, not volume. This is strange. For ordinary objects, entropy is proportional to volume. A bigger box can hold more information. But for black holes, surface area matters. This suggests that a space region's information content might be determined by its boundary rather than its interior. This idea was extended to a more general principle. The holographic principle says all information in a space volume can be encoded on that volume's boundary. The universe might be like a hologram where the three-dimensional world we experience emerges from information encoded on a two-dimensional surface. String theory provides some support for this. In certain models, there's a mathematical correspondence between a gravity theory in higher dimensional space and a quantum field theory without gravity on that space's boundary. This is called the AD-CFT correspondence, one of the most important discoveries in theoretical physics in the past 30 years. It suggests gravity and spacetime might be emergent, arising from a more fundamental quantum theory, not including space and time as basic ingredients. But even with the holographic principle, the information paradox wasn't fully resolved. The question remained, how exactly does information get out of the black hole? Hawking radiation is thermal, it's random. How can it carry information? In recent years, there's been progress. The key breakthrough came from thinking more carefully about what happens to entanglement as a black hole evaporates. When Hawking radiation is emitted, escaping particles are entangled with particles falling into the black hole. This creates correlations between the black hole's inside and outside. As the black hole evaporates, these correlations change in complex ways. In 2019 and 2020, a series of papers introduced the concept of quantum extremal surfaces and islands. The idea is that when you calculate Hawking radiation entropy, you need to include contributions not just from the radiation itself, but also from a region inside the black hole, an island correlated with the radiation. As the black hole evaporates, this island grows. Eventually it includes the entire black hole interior. At this point, radiation carries all information that fell in. Information is conserved after all. This led to resolving the page curve problem. Don Page calculated in the 1990s that if information is conserved, Hawking radiation entropy should initially increase as the black hole evaporates, but then decrease back to zero as the last black hole bits disappear. This is because early in evaporation, radiation is being emitted and carrying entropy away. But late in evaporation, as more information escapes, entropy should drop. The radiation becomes more and more correlated with what fell in. For decades, no one could explain how this page curve could arise from black hole physics. But recent work on islands shows the page curve emerges naturally when you calculate carefully. Radiation entropy follows exactly the curve Page predicted. Information is preserved. Does this mean the information paradox is solved? Most physicists think we're very close, but there are still details to work out. The island calculation works in simplified models, but hasn't been fully proven for realistic black holes in our four-dimensional universe. There are also deeper questions about what it means for information to be encoded in Hawking radiation in such a complex way. Can information actually be extracted in practice, or is it scrambled so thoroughly it's effectively lost even if technically still there? But the progress is real. The black hole information paradox, which seemed like an unsolvable conflict between quantum mechanics and general relativity, is yielding to new ideas and new mathematics. And those new ideas point towards something profound. Space-time and gravity are not fundamental. They emerge from quantum entanglement. Space-time fabric is woven from quantum correlations. And when we understand that connection fully, we'll have a quantum gravity theory. Why this matters? So why does all this matter? Why should you care whether space-time is made of loops or strings or entanglement? Why does it matter what happened at the Big Bang, or whether black holes destroy information? These seem like abstract questions far removed from everyday life, but solving these mysteries could change everything. First, understanding what spacetime is at the fundamental level would complete the reality picture physics has been building for centuries. Right now, we have two great theories. General relativity describes gravity and the universe's large-scale structure. Quantum mechanics describes particles and forces at small scales. Both theories are extraordinarily successful, tested countless times and never failed. But they can't both be right in their current forms because they contradict each other. General relativity treats space-time as smooth and continuous. Quantum mechanics says things are discrete and uncertain. General relativity is deterministic. If you know the universe's state now, you can calculate its state at any other time. Quantum mechanics is probabilistic. You can only calculate different outcome probabilities. These are fundamentally different worldviews, clashing when you try applying both to the same situation, like a black hole's interior or the Big Bang. A quantum gravity theory would unify these two physics pillars. It would give us a single consistent framework for understanding the universe at all scales, from smallest particles to larger structures. It would be the culmination of a quest ongoing since the early 20th century, and it would almost certainly reveal new physics, new phenomena we haven't imagined yet. History suggests major physics unifications lead to technological revolutions. When Maxwell unified electricity and magnetism in the 1860s, it led to radio, television, telecommunications, and all modern electronics. When quantum mechanics was developed in the early 20th century, it led to semiconductors, transistors, lasers, and computers. Every piece of modern technology relies on quantum mechanics. When Einstein developed relativity, it seemed abstract and impractical, but GPS satellites rely on relativistic corrections. Nuclear energy comes from Einstein's equation E=mc2, showing mass and energy are equivalent. A quantum gravity theory could lead to technologies we can't even imagine right now. If spacetime is quantized, maybe we could manipulate it. Maybe we could create artificial gravity or control time flow. If wormholes can exist and be stabilized, maybe we could use them for travel or communication. If the multiverse is real and we could access other universes, possibilities would be limitless. Now, these are all wild speculations. We have no idea if any of this is possible. Most physicists think it's probably not. The energy scales involved in manipulating spacetime at the quantum level are so high we might never harness them practically. But the point is, we don't know. And history shows understanding fundamental physics often leads to applications no one predicted. More importantly, understanding spacetime would answer some of the deepest questions humans have ever asked. Where did the universe come from? What happened before the Big Bang? Will the universe end? What happens inside a black hole? Why does time flow in one direction? Why are there 3 space dimensions and 1 time dimension? Why do physics laws have the form they do? These questions have fascinated humans for thousands of years. Every culture has origin myths, stories about how the world began. Every religion has grappled with time and existence nature. Philosophers have debated whether time is real or illusion, whether the universe had a beginning or has always existed. For most of history, these questions were in philosophy and religion's realm. Science couldn't address them. But now, we're close. We have mathematical frameworks. We have observational data. We have theoretical tools that might let us answer these questions definitively. A quantum gravity theory could tell us what happened at the Big Bang. It could describe black hole interiors. It could explain why time exists and why it flows forward. These aren't just scientific questions. They're existential questions about reality's nature itself. There's also something philosophically profound about the fact that space-time might not be fundamental. We experience space and time as the stage on which everything happens. Objects exist in space. Events happen in time. Space and time seem like reality's most basic features. The idea that they might be emergent, that they might arise from something more fundamental, challenges our deepest existence intuitions. It's similar to how we now know solid matter is mostly empty space. When you touch a table, you feel it as solid. But the atoms making up the table are mostly empty space with tiny nuclei and electrons. Solidity is an emergent property arising from electromagnetic forces between atoms. The table isn't fundamentally solid. Solidity is an illusion emerging at large scales. If space-time is emergent, then distance and duration might be illusions in the same way. At the deepest level, there might not be any space or time. There might just be quantum information, correlations between quantum bits, and space and time emerge from those correlations' pattern. This would be a radical shift in how we think about reality. The journey continues. So let's come back to where we started. Spacetime. Einstein's idea, modern physics foundation, the framework describing gravity, universe expansion, black holes, gravitational waves, and the Big Bang. An idea tested thousands of times and never failed. An idea we use every single day in GPS satellites, in our cosmos understanding, in the technology surrounding us. And yet, the fundamental mystery remains. We don't know what it's made of. We don't know if it's fundamental or emergent. We don't know what happened at the Big Bang when equations predict a singularity where physics breaks down. We don't fully understand whether black holes preserve information or destroy it, though we're getting close to an answer. We have equations describing its behavior, but we lack a complete theory explaining its true nature. This isn't a failure. This is where we are. This is human knowledge's frontier. Every great science idea eventually reaches a boundary where it can't go further without something new. Newton's laws reached that boundary when scientists started measuring light speed and Mercury's orbit. Quantum mechanics and relativity reached that boundary when scientists started thinking about black holes and the Big Bang. And now we're at the boundary again. We're at the place where Einstein's smooth spacetime meets the quantum world of particles and uncertainty. Somewhere beyond that boundary is the answer, a quantum gravity theory, a description of what spacetime is at the Planck scale, an understanding of what happened at universe beginning, the information paradox resolution, maybe a unified theory describing all forces and particles, maybe a multiverse, maybe something we haven't imagined yet. The physicists working on these problems today are standing at a cliff's edge, looking out into the unknown. They're using mathematics and creativity and centuries of accumulated knowledge to build bridges across the gap. Some bridges will fail, some will lead nowhere. But one of them might reach the other side, and when it does, when someone finally figures out what spacetime really is, it will change everything. So next time you use GPS or look at a black hole photograph or think about the Big Bang, remember this. You're looking at one of science's deepest mysteries. You're seeing evidence of something we use but don't fully understand. An idea working perfectly in practice but remaining mysterious in principle. Spacetime is real. We can measure it. We can photograph it. We can detect waves moving through it. But we don't know what it is, and that's okay. That's where adventure begins. That's where science happens. Not in answers we've already found, but in questions we're still trying to answer. Einstein gave us the spacetime idea over 100 years ago. It revolutionized physics. It explained gravity. It predicted black holes and gravitational waves and universe expansion. It's been one of history's most successful theories. But Einstein himself would probably be first to admit it's not the story's end. It's not the final answer. It's a step along the way. A beautiful, elegant, powerful step, but still just a step. The final answer is waiting. It's out there in the mathematics, in the experiments, in observations yet to be made. Someone will find it. Maybe in our lifetimes, maybe in the next generation, maybe centuries from now, but it's there. And when we find it, we'll look back at this time, this moment when we knew space-time exists but didn't know what it was, and we'll see it as the turning point, the moment just before everything changed. Thank you for joining me on this journey through space-time and its mysteries. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me continue making these deep dives into the cosmos. And remember, the universe is full of mysteries waiting to be solved. Space-time is just one of them, but it might be the most important one.